Hello, this is Xiaotian Liu, and this video for my final project. My topic is gradient descent. And firstly, I want to introduce the speediest descent. The speediest descent, like rolling a ball, and the ball will roll down in a hill. Sometimes the ball will stuck in a pot here, like local minimum for a function. And the question is, what's the direction the ball will roll in? Actually, for the function, the direction is minus grid f. The grid f will tell us which way in order to go up the hill as fast as possible. So minus grid f will tell us the fastest way to go down. And that is easy to understanding. So I want to introduce my code now. The first function is the gradient descent, named gradient descent. Actually is steepest descent. For here x, we have x, fxi, fx1, fx2, and x. X actually is the point we get the full start, and the return is the new x we get. And we can see an example here. We got the function, and we have fx1 here, fx2 here, and the diff is where decided how many times the code will run. That is the logic of the code. And when we run the code, we can have a lot of points, and we draw this point we can see here. The surface is not that clearly, so we can see here that more clearly of the plot. And we can see the shape of the point is like this. That was the steepest descent done, what it done. And the second example is same. And the third example actually is similar, but is high power function, so it may be run more times. And we can see after these three examples, we can see some disadvantage of the steepest descent. Firstly, we can see when the close to the minimum value, the speed will slow down. That is the biggest problem of that. So that will run the code a lot of times to get the minimum value. And the second problem is for some straight line, the steepest descent is not that good. And the third question is for some special function that maybe have the zigzag minimum. When we run the code, we will find that. So we have some way to modify that. Here is the modification part. Firstly, we consider the Newton's method to modify that. Newton's method is also a kind of gradient descent, but it's different to steep descent. That will be very fast in the when the point is close to the minimum. But at the start, that will be not that good because that's not the speediest direction to the minimum. So we can see here for the example. Actually, it's same to the second one, but we just use the Newton method so that we run more times than use the steepest descent, but we can see the picture when we close to the minimum. That is better than the steepest descent. So we consider to do our modification like that. At the start, we use the stepwise descent, and then when the point is very close to the minimum, we change the method to the Newton method, and that will go to the minimum directly, not like a zigzag shape like that. So here is the 5 example of the last example of this project. And we can see that's same to the that's the same function of the third example. And we can see here at the start we still use the steepest descent, so the shape is like this. But when we close to the minimum, we change to Newton, so that is directly to the go down to the minimum. And but because I think maybe because the diff is not small enough, so the time of the curve run is same. So if we can have a small diff, that maybe will have a better, that will perform better. That's all of my project of gradient descent. Thanks a lot.